There is a cold bruise in the oldest light in the universe, 1.8 billion light-years across. Physicists ruled out every normal explanation. What remains? Another universe physically struck ours before Earth existed, and the scar is still there. That is where this begins. But this video does not stop there. After the bruise comes the dark flow, something outside the edge of everything we can see, pulling our galaxies at 2 million miles per hour toward a source we cannot identify. Then the false vacuum, sitting beneath the ground of all existence, ready to collapse. Then your own body, splitting into thousands of versions of itself every second. If any of this holds, then what are you actually sitting inside right now? Subscribe. We are going to find out. Right now, while you sit wherever you are, your body is splitting. Your atoms, your neurons, the specific arrangement of matter that makes you you, all of it dividing into slightly different versions of itself, roughly 25,000 times every second. Every quantum event in your body, every electron jump, every particle interaction is forking you into a new branch of reality. One version of you keeps reading. Another version just stopped. Both are real. Both think they are the only one. This is called the many worlds interpretation. It is a confirmed mathematical framework derived directly from the Schrödinger equation with zero modifications. It does not require you to believe it. The math produces it whether you accept it or not. Hugh Everett III proposed it in 1957. He was a graduate student at Princeton. His advisor, John Wheeler, took the paper to Niels Bohr in Copenhagen. Bohr dismissed it. The physics community did not debate it, they buried it. Everett was effectively exiled from academic physics. He spent the rest of his life working on classified military research and drinking heavily. He died at 51. Sit with that for a moment. The man who looked at the equations and correctly described what was happening to your body every second of your life was publicly destroyed for saying so. After Everett died, something shifted. Physicists like David Deutsch and David Wallace started working through the implications. They found that the many worlds interpretation is not just consistent with the equations. It is the only interpretation that does not require you to add something extra to quantum mechanics to make the collapse happen. Every other interpretation cheats. Many worlds does not cheat. It just accepts what the math says, and what the math says is disturbing. Here is the chain. Quantum events are real. Quantum events produce superpositions. Superpositions, under many worlds, do not collapse. They branch. Your body is a quantum system. Therefore, your body is branching. Right now, every second you have been alive. Every second before you were born, the atoms that would eventually become you were already splitting long before they assembled into a person. The version of you reading this sentence is one path through a tree with more branches than there are particles in the observable universe. Each branch is equally real. Each branch contains a version of you that has no idea the others exist. Each of those versions is sitting somewhere, reading something, or staring at a wall, or already dead, believing with complete certainty that they are the original. There is no original. That concept has no meaning here. What you feel as your continuous self, the unbroken thread of memory and identity you carry through time, is a single branch of an incomprehensible structure. You are a thread. The fabric contains trillions of versions of this moment, and none of them can see each other, and none of them are wrong about existing. Physicists who take this seriously now number in the thousands. The interpretation is taught in graduate programs. It appears in peer-reviewed journals without apology, and here is where it stops being abstract. You are not observing this from the outside. You are inside it. The branching is happening in your chest right now, in the space between your heartbeats, in the firing of whatever neurons are processing these words. Hugh Everett saw this clearly in 1957. The establishment spent decades making sure you did not hear about it. The man who told the truth about what was happening to your body was silenced and died at 51. What does it mean that they worked so hard to stop you from knowing? In 1935, Albert Einstein published a paper with Boris Podolsky and Nathan Rosen. It is called the EPR paper. Einstein was brilliant, celebrated, and completely certain of his conclusion. The conclusion was this: quantum entanglement. The idea that two particles can be connected across any distance and instantly influence each other was impossible. It violated the speed of light. It violated locality. It violated everything physics knew about how cause and effect worked. Einstein called entanglement a spooky action at a distance and used it as proof that quantum mechanics was incomplete. He believed hidden variables, information we just hadn't found yet, were the real explanation. He was wrong. In 1972, John Clauser at the University of California, Berkeley ran the experiment. He built a device that generated pairs of entangled photons and measured their properties after separating them. The results matched quantum mechanics exactly. They violated Einstein's hidden variable model completely. Entanglement was real. The spooky action Einstein dismissed as absurd was a confirmed physical phenomenon. The physics establishment had been confidently wrong for 37 years. Clauser received the Nobel Prize in Physics in 2022, not for proving something new, for proving that the consensus had been wrong about something fundamental for nearly 4 decades. Think about what that means. The most celebrated physicist in history, supported by the majority of the field, looked at a real phenomenon and called it impossible. They built careers on that position. They wrote textbooks. They trained generations of students, and they were wrong. Now, ask yourself a simple question. What is the physics consensus confidently wrong about right now? This is not a rhetorical device. It is a structural observation about how physics has operated historically. Paradigms resist. Institutions protect their frameworks. Individual scientists who challenge consensus are isolated. Everett was ignored. Clauser himself, before his Nobel, struggled to find research funding because his work was considered fringe. The pattern is consistent. A phenomenon is observed. It challenges the dominant framework. The dominant framework fights back. Eventually, the evidence becomes impossible to ignore. The consensus shifts. And afterward, everyone agrees the new position was obviously correct all along. We are currently inside one of those cycles, possibly several simultaneously. The Hubble tension, which you will hear about shortly, is a 5 sigma anomaly in the expansion of the universe. That means there is roughly a 1 in 3.5 million chance it is measurement error. The consensus response has been to look for instrument problems. The alternative, that the standard model of cosmology is missing something fundamental, is resisted with the same energy the EPR consensus used to resist entanglement. The dark energy measurements from the Dark Energy Spectroscopic Instrument Survey in 2025 showed the cosmological constant may be changing. The consensus assumed it was fixed. The data says otherwise. The response has been cautious, qualified, careful, 37 years. That is how long it took for entanglement to go from impossible to Nobel-worthy. You are living through the equivalent moment. The data is already in. The anomalies are already measured. The papers are already published. And somewhere in the current consensus is a position that future physicists will look back on the way we look back at Einstein's dismissal of entanglement. The question is which position, and whether understanding that position, really understanding it, will feel like relief or like the flaw disappearing. Stop for a moment. Before the next piece of evidence, consider where you are right now. You are on a planet, inside a solar system, inside a galaxy, inside a structure of matter that formed from a single event roughly 13.8 billion years ago. Everything you know, every person, every idea, every war, every piece of music exists inside this structure. You have no way to step outside it. You have no frame of reference from outside it. You are, in the most literal sense possible, trapped inside a universe you cannot exit and cannot fully see. Now, There is a number that describes how fast that universe is expanding. It is called the Hubble constant. Getting it right matters enormously because it tells us the age of the universe, its structure, and its eventual fate. Physicists have two completely independent ways of measuring it. The first method starts from the cosmic microwave background, the oldest light in the universe. It uses the standard model of cosmology to predict the expansion rate from that ancient light. That measurement gives a value of approximately 67 kilometers per second per megaparsec. Write that number in your head. The second method measures distance markers called Cepheid variable stars and type 1a supernovas in the current universe. That measurement, led by Adam Rees at Johns Hopkins University, consistently gives a value of approximately 73 kilometers per second per megaparsec. Those two numbers should be the same. They are measuring the same universe. They use different instruments, different methods, different starting points, and they disagree by approximately 9%. 9% does not sound catastrophic until you understand that the gap is 5 sigma. In physics, 5 sigma means the probability that this disagreement is random error is roughly 1 in 3.5 million. 5 sigma is how physics defines a discovery. When the Higgs boson was confirmed, it was 5 sigma. This gap is 5 sigma, except what it is confirming is that something is deeply wrong with the model. Adam Rees described it plainly. He called it a crisis in cosmology. That language is deliberate. Physicists do not use the word crisis unless the situation demands it. Two possible explanations sit on the table. The first, our instruments and models have some unknown systematic error that has survived every attempt to find it for over a decade. The second, the standard cosmological model is missing something that affects the expansion rate, something that was not in the equations. If the model is missing something, that something must be physically real. It must be out there, and several physicists have pointed at a specific possibility. That something outside the observable universe, something we cannot see and cannot measure directly, is exerting influence on the expansion of the space you are currently sitting inside. Think about that. If our model is broken, the break might be caused by physics happening beyond the edge of everything we can observe. Something our telescopes will never reach is affecting the universe your body exists in right now. A crisis in cosmology is a crisis in the floor beneath your feet. When the expansion rate is wrong, the story of what this universe is and where it is going is wrong, and we do not yet know how wrong. Here is something the standard model of cosmology assumed for decades. Dark energy is constant. It fills space uniformly. It does not change over time. It is a fixed property of the vacuum itself, a number you could write down once and trust forever. That assumption was comfortable. It made the equations simpler. It matched the data well enough. Cosmologists built the entire architecture of our understanding of the universe's fate on that assumption. In 2025, the Dark Energy Spectroscopic Instrument Collaboration released its full analysis. They had mapped the positions and velocities of 15 million galaxies across the history of the universe. 15 million individual galaxies, tracked across cosmic time. This is the largest three-dimensional map of the universe ever constructed. It was built specifically to measure how dark energy has behaved as the universe aged. The result? The data shows 4.2 sigma evidence that dark energy is weakening. The cosmological constant is not constant. The force that determines the structure and fate of the universe is changing over time. 4.2 sigma means the probability of this being statistical noise is roughly 1 in 100,000. It is just below the 5 sigma threshold physicists use to call something a confirmed discovery. But it is close, and critically, it is directional. The signal does not scatter randomly. It consistently points the same way, toward weakening. Multiple independent analyses of the same dataset reach the same conclusion. The direction does not change when you recheck it. If dark energy is weakening, the question is what it is weakening toward. There are a few theoretical destinations. One of them is zero. Dark energy weakens to zero, and the expansion of the universe slows and eventually halts. Another destination is negative. Dark energy crosses zero and becomes a contracting force. In that case, the universe collapses inward. Galaxies that have spent billions of years separating begin to approach each other, then merge, then compress. But there is a third possibility that connects directly to what you heard in the previous chapter about the Hubble tension. Dark energy is not a fixed property of the vacuum. It is a field that can evolve, that can interact, that can be influenced. Some models call it quintessence. In those models, dark energy's behavior is not determined by the internal state of our universe alone. It can be affected by conditions outside. Right now, in your chest, in the space between your atoms, dark energy is present. It is not a thing you can touch. It is a property of the space itself, everywhere, including the space your body occupies. And the property is shifting. Whatever value it holds today, it held a slightly different value a billion years ago. It will hold a different value a billion years from now. The measurement was not made by a fringe team. The Dark Energy Spectroscopic Instrument is a collaboration involving over 900 scientists at more than 70 institutions. This is the mainstream. This is the consensus doing its own measurements and discovering that its foundational assumption was wrong, 4.2 sigma, across 15 million galaxies. The constant is not constant. The force holding the architecture of the universe in the configuration that permits your existence is losing strength. The building's foundation is not what the builders thought it was. And the most disturbing question is the one that follows directly. If it is decaying, it must be decaying towards something. Decay implies a direction. Direction implies a destination. And whatever that destination is, the laws of physics that currently allow atoms like yours to exist may not survive the arrival. You know the Higgs boson from the headlines. The announcement came in July of 2012. The experiment was at the Large Hadron Collider in Geneva. The particle was found. The standard model of particle physics was confirmed. The world applauded. The physicists celebrated. Nobody explained what the measurement actually meant about the ground you are standing on. The Higgs boson's mass came in at approximately 125 giga-electron volts. That specific number, combined with the measured mass of the top quark, places the universe's vacuum in a very particular position on what physicists call the vacuum stability diagram. That diagram plots whether the vacuum of our universe, the quantum field state that all matter in existence sits on top of, is stable, metastable, or unstable. 125 giga-electron volts puts us in the metastable zone. This is confirmed. The calculation has been independently checked many times by multiple groups. The physicists who worked on it are not fringe. They published in Physical Review Letters and Physical Review D. The math checks out. Metastable means this. The vacuum of the universe is a local energy minimum. A low point, a trough, but it is not the lowest possible point. It is a temporary resting place. Imagine a ball sitting in a shallow depression partway down a hill. The ball is stable in that depression under normal conditions. It will stay there. It has been staying there for 13 billion years. But the depression is not the bottom of the hill. The bottom exists somewhere lower. And if the edge of the depression is breached, the ball rolls. The ball is everything, every particle, every force, every atom in your body. The depression is the vacuum state of the universe. The bottom of the hill is a vacuum state, where the fundamental constants of physics take different values, where the relationships between the electromagnetic force and the weak force are different, where the mass of electrons is different, where atoms, as they currently exist and hold together to form molecules and cells, and you, cannot exist in any form. When physicists talk about a vacuum decay event, they mean this. Somewhere, a quantum fluctuation punches through the wall of the depression. A bubble of true vacuum, the real lowest energy state, nucleates. That bubble expands outward at exactly the speed of light. Inside it, the constants of physics are different. Everything that depended on the old constants ceases to function. There is no warning. The bubble wall arrives at the speed of light, which means you cannot outrun it, cannot detect it coming, and would have zero time between its arrival and the end of all atomic structure in your body. You would not experience it. There is no experience after the bubble wall passes. The atoms that make you up would simply no longer be able to hold the configuration they are in. This is a theoretical conclusion with confirmed experimental input. The Higgs mass is measured. The top quark mass is measured. The stability calculation follows from those values. The conclusion is metastable. This is the mainstream physics position, not a fringe hypothesis. Your cosmological address is a temporary configuration that happens to support atoms, chemistry, and the conditions for your existence. It is not the universe's lowest energy state. It is where things happen to be sitting right now. The ground beneath all existence is a ledge, and you cannot see what is below it, because nothing from below can survive the crossing to tell you. There is a photograph of the universe's infancy. It was taken not with visible light, but with microwave radiation. It is called the cosmic microwave background. It was formed 380,000 years after the beginning, when the universe had cooled enough for electrons to bind to protons and space became transparent for the first time. That light has been traveling ever since. It comes from every direction. It is the wallpaper of the universe. When you aim any sensitive microwave receiver at any patch of sky, you are looking at this same ancient light. The cosmic microwave background is the oldest thing you can observe. Every telescope pointed into the depths of space. Every satellite launched to map the early universe eventually hits this. It is the wall beyond which direct observation cannot reach. And it has a wound. In the southern hemisphere of the sky, there is a region of the cosmic microwave background that is colder than its surroundings by about 70 microkelvin. That does not sound like much until you understand that variations in the cosmic microwave background are tiny to begin with, and this anomaly is enormous. It spans roughly 1.8 billion light-years across. That is the cold spot. It was detected with statistical significance in multiple independent analyses. The Wilkinson Microwave Anisotropy Probe saw it. The Planck satellite confirmed it. It has been examined from dozens of angles, using different data reduction methods, different teams, different assumptions. It is real. The probability of it arising from normal statistical variation is less than 2%. Something is wrong with that patch of sky. The oldest light in existence carries a mark that should not be there. Right now, as you sit in your room, the microwave radiation from that region is passing through your body. The ancient light from the edge of everything observable is moving through the molecules of your hands, your lungs, your eyes. It has been doing so since before the Earth existed, and it carries this anomaly with it. A cold patch in the oldest photograph of the universe, passing through you without leaving a trace, having crossed a billion light-year wound to reach you. The cosmic microwave background is not supposed to have features like this. The standard model of cosmology, the lambda cold dark matter model, generates simulations of what the cosmic microwave background should look like. Those simulations can generate a feature this large and this cold approximately 1 to 2% of the time. That is not zero. But cosmologists do not shrug at a 1 to 2% anomaly in their most fundamental dataset. They look for explanations. For years, they had one. It was called the supervoid hypothesis. There was a region of space between us and the cold spot with fewer galaxies than normal, a void. Light loses energy passing through a void due to a process called the integrated Sachs-Wolf effect. A sufficiently large and empty void could in principle cool the light. It was a tidy explanation. The oldest photo of the universe has a wound in it. They thought they knew what caused it. They were about to find out they were wrong. Take a step back from the data for a moment. You have heard about branching realities, confirmed experimental violations of classical physics, a crisis in the expansion rate, decaying dark energy, and an unstable vacuum. Each of these is an independent problem. Each has its own measurements, its own researchers, its own literature. None of them depend on the others to be real. What is remarkable is not that any single one of these anomalies exists. What is remarkable is that they all exist simultaneously. Science does not expect this. When a model is basically correct, anomalies appear occasionally and resolve with more data. When multiple independent anomalies cluster together, persist for years, and resist every attempt at resolution, it typically means the model is missing something structural, something foundational, something that, once found, will reclassify everything above it. You are living at the moment when the missing structure is starting to produce visible cracks. The data is already collected. The papers are already published. The question being asked in cosmology right now is not whether something is wrong. It is what kind of wrong and how deep it goes. Now, back to the cold spot. The supervoid explanation had one job: account for the temperature deficit. A team led by Tom Shanks at Durham University set out in 2017 to confirm it. They used the Vista Hemisphere Survey, a systematic photometric redshift survey covering the sky region around the cold spot in detail. This was a serious, professional, observational effort, the kind of work designed to close a question and move on. They found the supervoid. It is real. There is a region with lower than average galaxy density in the direction of the cold spot. The void exists exactly where it was predicted to exist. For a moment, it looked like the question was closed. The problem is scale. The supervoid they found is far too small and too shallow to produce even 20% of the observed temperature anomaly. The integrated Sachs-Wolf effect from that void, the only mechanism by which the void could cool the light, accounts for a minor fraction of the total temperature deficit. More than 80% of the anomaly remains without an explanation that fits inside our universe. The supervoid explanation was not weakened by the Shanks team study. It was ruled out as a sufficient cause. There is a difference. Weakened means it still partially works. Ruled out as sufficient means the cold spot is not from here. Think about what this means procedurally. A major anomaly in the oldest light in the universe, confirmed by 2 independent satellite missions using different instruments and different analysis pipelines, spent years being explained away by a hypothesis that turned out to account for a small fraction of the effect. The cosmology community spent time and resources pointing at that hypothesis, building it up, treating it as the likely answer. The comfort was false. The cold spot is larger, colder, and more anomalous than anything our model should produce. The only explanation that has been ruled out is the most comforting one. When the comfortable explanation fails and nothing from inside the universe fits, the question becomes, what sits outside the universe that could produce this? We spent years pointing at an explanation. The explanation was not enough, and the gap it leaves behind is not a small one. In 2025, a paper appeared in Physical Review Letters. The authors had taken the Planck satellite's data on the cold spot and modeled it using several competing hypotheses. They tested the supervoid with updated parameters. They tested pure statistical fluctuation models. They tested a third candidate, one that had been discussed theoretically for years, but never formally evaluated against the data with this level of rigor. That candidate was a bubble universe collision. The paper's conclusion: when you rank the competing explanations by how well they fit the observed data, the most statistically favored is a physical interaction between our universe and another bubble universe. This is speculation, but it is quantitatively motivated speculation. The math checks out better for the collision model than for the alternatives currently on the table. Here is what a bubble universe collision means in physical terms. The eternal inflation model, developed by Alan Guth at the Massachusetts Institute of Technology and extended by André Linde at Stanford University, describes our universe as one bubble that nucleated inside a larger, inflating space. The larger space keeps inflating indefinitely. New bubbles of universe constantly form inside it. Each bubble has its own physical constants, its own initial conditions, its own version of the laws of physics. Most bubbles never interact. They expand in their own directions inside the larger inflating space and never intersect. But the larger space is producing them continuously, and the geometry of that space allows bubbles that happen to expand toward each other to collide. The collision does not destroy either universe. The bubbles do not pop like soap bubbles. They graze. The contact region undergoes a violent disturbance in energy density. That disturbance propagates into both universes. In our universe, if the collision happened in the very early plasma, before the cosmic microwave background was formed, the disturbance would leave a fingerprint in the temperature distribution of that oldest light. The cold spot's shape, size, and temperature profile fit the collision fingerprint better than they fit any internal explanation. The microwave radiation carrying that fingerprint is passing through your body right now. It has been traveling for 13.5 billion years from the edge of the visible universe to reach you. It passed through the Planck satellite's detectors. It has been analyzed. The mark is real. The paper models the collision as a past event, something that happened near the beginning and left a static scar. The scar does not move or grow in the current data. But the paper does not close the larger question. Eternal inflation does not produce one bubble per era and then stop. It produces bubbles continuously. If our universe has already been struck once, the eternal inflation model that predicts that collision also predicts that new bubbles are forming and expanding right now in the space surrounding our universe. The boundary of our universe exists. It is real, and the probability that nothing is currently approaching it, given what the 2025 paper found, is not addressed. Finding a scar tells you the collision process is real. It does not tell you it ended. If the collision happened once, is it still happening? In 2015, Ranga Ramchari, a researcher at the California Institute of Technology, was working through the residual signal in the Planck satellite's data on the cosmic microwave background. After removing all the known foregrounds, all the dust, all the galactic emission, all the modeled sources of microwave radiation, a residual was left. Residuals are expected. They are usually noise. This residual was not noise. Cherry found a bright blob, specifically a cluster of signals approximately 4,500 times brighter than the standard model of cosmology predicts for that region of sky, 4,500 times. That is not a calibration error. That is not a systematic bias. That is an object or a phenomenon that does not fit any category in the current model. But the brightness alone is not the most disturbing part. The disturbing part is the spectral signature. Different types of matter produce different spectral signatures. The mix of photons to matter particles in our universe has a specific ratio. It was set in the first seconds after the beginning by the conditions of our particular universe's formation. That ratio is one of the defining numbers of our cosmological model. It is the same everywhere you look in our universe. Every galaxy, every cluster, every gas cloud. The ratio is consistent. The blob has a different ratio. The matter-to-photon ratio in the blob is approximately 65 times larger than anywhere else in the observable universe. 65 times. That is not a variation. That is a different value entirely. The kind of value you would expect from matter that formed under different initial conditions. Matter that did not form in our universe. Chari was careful in his published paper. He described it as a possible signal from a collision with another universe. He did not overclaim. He called it speculative. But he put the number in the paper, 65 times the expected ratio. The math checks out. The blob is in the sky right now. The light from it passed through the Planck satellite's detectors. It has been catalogued. It has been sitting in the published literature since 2015. The explanation that fits the data best is matter from somewhere else. With physics we did not generate. There is a patch of sky where the light has the wrong chemistry, and the wrong chemistry matches what you would expect from matter that formed in a different universe entirely. In 2008, Alexander Kashlinsky at the National Aeronautics and Space Administration Goddard Space Flight Center published a study in the astrophysical journal Letters. He had been looking at the motion of galaxy clusters across the sky, not their recession from cosmic expansion, but their peculiar velocities, the movement on top of expansion, the motion caused by gravitational attraction. He looked at 800 galaxy clusters. They were all moving in the same direction, all 800 of them, moving at approximately 2 million miles per hour toward a single region of sky, a region in the direction of the constellations Centaurus and Vela, a region that contains nothing unusual visible to our telescopes, a region that is, by every observation we can make, empty. Kashlinsky named it the dark flow. The name is deliberate. The flow is real. The direction is consistent. The speed is uniform. But the uniform speed is the part that should not exist. In normal gravitational dynamics, the strength of an attraction falls off with distance. The clusters closest to the source should be moving fastest. The clusters farther away should be moving slower. The speed should drop with distance, according to the inverse square law. The speed does not drop with distance. Across hundreds of millions of light years of separation, the clusters all move at the same speed. That behavior cannot be produced by anything inside the observable universe. The source of the gravitational pull, if it is gravity, is outside the observable universe, beyond the boundary, beyond the edge of everything our instruments can reach. Something on the other side of the observable universe is pulling on every cluster Kashlinsky measured, something so massive or so energetically dominant that its gravitational influence crosses the cosmological horizon and reaches inside. The observable universe is roughly 93 billion light-years across. The horizon is the maximum distance from which light has had time to reach us. Beyond it, space exists. We know this because the universe did not stop at our horizon. It kept going. But nothing from beyond the horizon has had time to reach us in the age of the universe, except the pull does not care about the light travel time. Gravity, or whatever is causing the dark flow, is reaching across the boundary right now, reaching into the universe your body exists in, tugging on 800 clusters of galaxies with a force consistent enough and large enough to produce a measurable directional signal across hundreds of millions of light years. This is confirmed. The observation is real. Multiple subsequent analyses have examined the dataset. The dark flow persists. What is causing it remains unknown. Something outside everything you can observe is gravitationally pulling the matter of your universe toward it. Right now, the galaxy clusters are already moving. They have been moving for billions of years. And whatever is pulling them is large enough, persistent enough, and close enough in some dimension we cannot perceive to make 800 galaxy clusters move in lockstep toward a single point. Something on the other side of the observable universe is pulling toward it. And it has not stopped. Hugh Everett III was 27 years old when he sat down at Princeton and wrote the most unsettling idea in the history of physics. He called it the relative state formulation. What it described was this: the universe never collapses into one outcome. Every quantum event that can go two ways goes both ways. Both branches are real. Both versions of you continue. He typed this up, defended it, and then watched the physics establishment try to erase him. His advisor was John Archibald Wheeler, one of the most respected physicists alive. Wheeler liked the idea. Wheeler was also alarmed by it. Alarmed enough that before Everett could present his work publicly, Wheeler traveled to Copenhagen and pre-negotiated with Niels Bohr's group. He was not asking for their approval. He was trying to soften the blow. What came back from Bohr's camp was contempt, not skepticism, contempt. Bohr's group called it incoherent. They said it failed to solve the measurement problem. They said it was bad physics dressed up in philosophical clothing. The pressure on Everett was immediate and enormous. He revised his thesis. He cut the most radical sections. He submitted a shorter, quieter version. He got his degree, and then he walked out of academia and never came back. This is the part that should disturb you. The mechanism that forced him out was not a refutation. No one proved him wrong. No experiment contradicted his math. He was pushed out because the established view held the chairs, the journals, and the grant funding. And the established view did not want this question on the table. Everett went to work for the Pentagon. He spent the rest of his life doing weapons research. He drank heavily. He became largely invisible to the field he had tried to reshape. He died at 51 in 1982 from a heart attack. Per his wishes, his ashes were thrown in the trash. Sit with that. In 1996, his daughter Elizabeth died by suicide. She left a note. In it, she wrote that she hoped to be placed in a parallel universe with her father. She was not using poetry as comfort. She was using the literal language of the theory her father had died believing in. That is what his life left behind. A daughter who understood many worlds well enough to name it in her final words. His son is Mark Everett. You may know him as the lead singer of the band Eels. Mark found his father's work in cardboard boxes in the basement, not organized, not archived, just stacked in boxes, next to the things people put in basements when they do not know what to do with something. Mark had to learn who his father was from those boxes, after his father was already dead. Here is what makes this more than a sad story. By the time Mark found those boxes, physicists had been quietly returning to Hugh's work for decades. The many worlds interpretation had been circulating in graduate programs, showing up in papers, getting serious treatment in quantum computing research. The establishment had not reversed, but the tide had shifted. The man who was expelled for saying the universe branches was being quietly rehabilitated while his son sorted through his things in a basement. The theory did not die when Everett did. The question is whether that should comfort you or make you more afraid. Because if Everett was right, there is a version of him that never left academia, and there is a version of you sitting somewhere else right now, reading something entirely different, having made a choice today that you did not make here. How many versions of you exist right now that you will never know about? Right now, as you are reading this, your body is branching the universe. This is the mechanism. Understand it clearly, because the implications do not stop at physics. Every radioactive atom in your body decays at a moment determined entirely by quantum probability. There is no deeper cause. There is no hidden clock. The atom decays when it decays because quantum mechanics says the decay event is genuinely undetermined until it happens. When it does happen, in the many worlds framework, the universe does not pick one outcome. It accommodates both. The branch where the atom decayed and the branch where it did not both continue forward as equally real physical histories. Your body contains approximately 7 billion atoms. A meaningful fraction of those are radioactive isotopes, including carbon-14 and potassium-40. They are decaying right now, inside you, and each decay is a branching event. The estimates put the total number of branching events generated by your body alone at approximately 25,000 per second. 25,000 times per second, the universe divides over something happening inside your skin, but you feel none of it. And that is the disturbing part, confirmed by quantum mechanics, confirmed by the process called decoherence. When a quantum system interacts with its environment, the branches separate. They stop interfering with each other. They become causally isolated. The timescale for a dust grain to decohere from its environment is 10 to the negative 31st seconds. That is not a slow process. That is instantaneous by any standard a human body can register. The branch where a particle in your retina went left and the branch where it went right are separated before any signal from that event has traveled a single millimeter. You cannot detect the branching because you are inside one branch. The moment the split occurs, you are already committed to one path. The other version of you is already gone, already embedded in a separate history that will never intersect with yours again. Here is what that means for your life. There are branching events happening in your neurons right now, quantum processes in synaptic proteins, in ion channel openings, in the electrochemical gradients that determine whether a neuron fires. If those events branch the universe, then there are versions of you right now in which your next thought was different, in which the decision you made this morning went the other way, in which the moment that changed your year happened differently. You did not choose between those outcomes. The universe chose for you by copying itself, and here is the part that should make you stop. There is no version of many worlds in which you survive everything. The branching is random. Some branches contain a version of you that will be diagnosed with something this year. Some branches contain a version of you that will not make it to the end of this decade. Those branches are real. They are happening right now in parallel with this one. You cannot feel them because decoherence seals them off before the signal even forms. You cannot feel the moment the universe splits into a version of you that does not survive. If you felt it, you might be able to refuse, but you cannot feel it. And there is no refusing. So what do you do with the knowledge that you are, at this moment, dying in some number of parallel branches, and that version of you felt nothing different in the seconds before it happened? For most of the 20th century, the people in charge of physics called many worlds theology. The word they used matters. Theology means belief without proof. Theology means you have left science and entered faith. By calling it theology, they were not just disagreeing with Everett. They were placing his work outside the boundary of legitimate inquiry. You were not allowed to take it seriously if you wanted a career. This is the philosophical reset. Pay attention to what actually happened. The interpretation that beat many worlds was called the Copenhagen interpretation. It was assembled by Niels Bohr and Werner Heisenberg in the 1920s. It said that a quantum system exists in superposition until you measure it. At the moment of measurement, the wave function collapses into one outcome. The other outcomes disappear. The universe picks one and discards the rest. That interpretation became the official view. It was in every textbook. It was what every physics student was taught. And it contained a problem that its defenders never solved. Not in the 1920s, not in the 1950s when Everett pushed back, not in the 1990s, not today. The problem is this: what counts as a measurement? What causes the collapse? Is it a conscious observer? Is it any physical interaction? The Copenhagen interpretation requires collapse to happen, but it never specifies the mechanism. It draws a line between quantum systems and classical observers, but it never explains where that line sits or why it exists. Many worlds does not have this problem. It simply removes the collapse entirely. The wave function never collapses. Every outcome occurs. The observer becomes entangled with the system and branches along with it. There is no measurement problem because there is no special role for measurement. By 2024, a major academic anthology emerged from a workshop held at Tel Aviv University. The anthology treated many worlds as a mainstream position in the foundations of physics. Serious chapters, serious authors, graduate-level treatment. The interpretation that was called theology in 1957 is now assigned reading in physics programs at research universities. Nothing was proved. No experiment settled it. What changed was that enough physicists looked at the Copenhagen interpretation's unsolved problems and decided that an interpretation requiring a mechanism it cannot specify is harder to defend than one that requires no mechanism at all. This should unsettle you in a specific way. The official view of reality, the one that determined what questions were allowed, the one used to bury Everett's career, held its position for decades without ever answering its central objection. The science did not change. The politics of the field changed. And now the view they called theology is the view being taught to the next generation of physicists. Ask yourself, if the field was wrong about that for 60 years, what is it wrong about right now? In 2016 and again in 2018, a machine in Antarctica detected something that should not exist. The instrument was called the Antarctic Impulsive Transient Antenna. It was a balloon-mounted radio telescope floated above the Antarctic ice to catch the faint radio signals produced when high-energy particles slam into the ice sheet and create particle showers. The instrument was looking up at the sky. It was designed to catch particles coming down from space. It caught particles coming up from the ground. Two separate events, separated by years, showed tau neutrino-like particles traveling upward through the Antarctic ice and exiting from the surface below the instrument. Confirmed by the team, published in peer-reviewed literature, cross-checked against the detector's calibration data, the signal was real. Here is the problem. Particles of that energy level cannot pass through Earth. The planet is too dense. An ultra-high-energy cosmic ray neutrino, traveling up through 4,000 miles of rock and iron core, loses so much energy through interactions that it cannot produce the kind of exit event the instrument detected. The math on this is not ambiguous. The cross-sections are well measured. You cannot get a signal like that from a particle that came from space, traveled down through the crust, survived the core, and came back out the other side at that energy. The conventional explanations were checked. Systematic errors, misidentified backgrounds, reflected signals from the sky that confused the detector's directional readings. The team considered all of them. The event survived the scrutiny. In 2018, a team including Luis Ankudokwi published a paper examining what could produce upward-traveling particles of that character at those energies. One of the leading explanations they presented was a CPT symmetric mirror universe. The paper went through peer review. It is in the literature. CPT symmetry is not a speculation. It is one of the best tested principles in all of particle physics. Every confirmed interaction in the standard model preserves CPT. The acronym stands for the combination of charge conjugation, parity transformation, and time reversal. The claim in the Ankudokwi paper was that a universe where all three are inverted simultaneously would be consistent with known physics, would exist in a kind of paired symmetry with ours, and could produce particles that enter our space-time from below. The anomalous events have not been explained away. They have been sitting in the literature for years, unresolved, while the field produces competing papers that attempt to account for the signal without invoking a mirror universe and have not yet succeeded. Right now, underneath the ice in Antarctica, something is sending particles upward through the ground. The leading physics explanation for where those particles are coming from is a universe that is the mirror image of ours, one running beneath us, hidden by the fact that it interacts with our matter in only one way, and that one interaction is gravity. If something is pulling on you from below, and that something is a universe, what exactly is the ground you are standing on? Take a moment here, because what comes next requires you to hold several things at once, and the picture only becomes disturbing when you see them together. A CPT symmetric mirror universe is not a metaphor. The proposal, developed seriously by Neil Turok and others, describes a universe where charge is reversed, parity is flipped, and time runs backward. The combined transformation, CPT, is the one symmetry that particle physics says the laws of nature respect at the deepest level. If the laws respect it, then a universe that is the CPT reflection of ours is not forbidden. It is, by the logic of the known laws, permitted. What would that universe look like? It would be made of antimatter. Its time arrow would point in the opposite direction from ours. Processes that move forward in our timeline would move backward in that one. Entropy would increase in the opposite direction. And because the gravitational interaction does not care about charge or parity or the direction of time, it would interact with our universe gravitationally. Mass is mass. Gravity reaches across the CPT transformation. Now think about where that universe would be. Turok's model places the mirror universe not somewhere distant in space, but paired with ours at the moment of the Big Bang, like two sides of a single creation event. In that picture, our universe and its mirror image nucleated together from a single point. They expand away from each other through time. Our time runs forward, its time runs backward, and the boundary between them, the surface they share, is the Big Bang itself. This means that down, the direction toward Earth's core, is also the direction toward the past of a reversed universe. The ground under your feet is not just rock. It is, in this model, also the interface between our space-time and a universe running in the other direction. Your body is in gravitational contact with that mirror right now. Confirmed, gravity couples to mass regardless of charge, parity, or time orientation. The rest of the picture is theory, but the math checks out. Though the upward particles came from below, the mirror universe model accounts for particles below. The gravitational connection to that mirror is not blocked by anything. There is no shield between your feet and whatever is on the other side of the event that created this universe. You have spent your entire life standing on the ground and thinking of it as solid, as a surface, as the bottom of your world. But the ground has a direction. Down is toward the center of the planet, down through the core, down through the other side. And in the model that currently best explains those anomalous signals, down is the direction of a universe that is the reversal of everything you are, a universe of antimatter, running backward through time, pulling on your body with its gravity right now. Does it feel different to stand up when you understand what you are standing over? Alan Guth was not trying to discover the multiverse. In 1981, he was trying to solve three specific problems with standard Big Bang cosmology. Why is the universe so flat? Why is it so uniform in temperature across regions that should never have been in contact with each other? And why are there no magnetic monopoles? Guth's solution was inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang, fast enough to smooth out irregularities and dilute any monopoles to imperceptibility. The math worked. The inflation model solved all three problems. And then it produced something nobody asked for. When Andre Linde and Paul Steinhardt examined the inflation model in 1982 and 1983, they found that the inflating field does not stop everywhere at once. It stops locally, in regions where the field rolls down to its minimum. But outside those regions, inflation continues. The background keeps expanding. New bubbles of stopped inflation form inside the ongoing expansion. Each bubble cools, develops its own physics, becomes a pocket universe. And the background keeps going, spawning more bubbles, forever. Guth himself described the result plainly. Most versions of inflation lead to eternal inflation, producing a number of pocket universes. He did not want this conclusion. It was forced on the mathematics. Here is what that means. Our universe is one bubble. It nucleated from an inflating background vacuum at a moment we call the Big Bang. The Big Bang was not the beginning of everything. It was the beginning of us, the moment our particular bubble stopped inflating and started cooling into the physics you are made of. Outside our bubble, the background was still expanding when our Big Bang happened. It may still be expanding now. Other bubbles exist. They formed before ours. They formed after ours. They are forming right now, outside our observable horizon, in a background we can never reach and will never see. Each one is a separate universe with its own laws, depending on what vacuum configuration it settled into when inflation ended. This was not the goal of inflation theory. The multiverse was not a prediction physicists went looking for. It is a prediction the equations produced when you followed the math to its end. Linde, Steinhardt, and Guth did not set out to populate the cosmos with pocket universes. The pocket universes were there in the equations from the beginning, and the equations were derived from the same particle physics that describes your body. Our universe did not choose to exist. It nucleated, the way a bubble nucleates in boiling water. You did not choose to be inside it. The question is, what happens to bubbles? Sidney Coleman and Frank DeLucia wrote their paper in 1980. It was not widely read outside specialist circles. What it described was a mechanism for the end of everything, and it described it with the calm precision of a maintenance report. The argument starts with the Higgs field. The Higgs field fills all of space. Your body interacts with it right now. It gives mass to the particles you are made of, and it sits at what appears to be a stable energy value, the value that defines the physics of our universe. But the measurements of the Higgs field's potential, confirmed by experiments at the Large Hadron Collider and detailed in papers throughout the 2010s, indicate that this value may be a false vacuum, a local minimum, stable for now, but with a deeper, true vacuum available at a different field value. If the field reaches the true vacuum, everything changes. The constants of physics change. The masses of particles change. The strength of forces changes. Chemistry becomes impossible. Atoms as you know them cease to exist. You cease to exist. Everything ceases to exist in any form that resembles the present universe. Coleman and DeLucia showed how this transition happens. A bubble of true vacuum nucleates spontaneously, somewhere in space, at random. It could happen anywhere. There is no location more likely than any other. Once formed, the bubble wall expands outward at the speed of light. Inside the wall, the new vacuum. Outside the wall, the old physics. For as long as the old physics remains, the wall is invisible. It emits no light. It carries no signal. It travels at the maximum speed any signal can travel. There is no warning because there is no way to construct a warning that moves faster than the thing you are warning about. Stephen Hawking, in his 2018 book, wrote that the Higgs potential has the worrisome feature that it might become metastable at energies above 100 billion electron volts. The word he chose was worrisome. For Hawking, that is not rhetoric. That is a physicist using the word that fits. The bubble could be forming right now, 1,000 light years away, or 1,000,000, or 10 feet from your face. You would not know until the wall reached you. And at the moment it reached you, the knowing and the ending would happen at the same time. There is a version of this process in which the bubble has already nucleated somewhere in our observable universe. The math does not rule it out. The estimates of how likely nucleation is per unit volume of space per unit time are not zero. How far away would the nearest bubble have to be for you to finish reading this sentence? In 2023, a team of physicists at Newcastle University and collaborating institutions created a system of ultra-cold atoms in a state called a Bose-Einstein condensate. They engineered the condensate to sit in a false vacuum state, a local energy minimum with a lower energy state available. Then they waited. The results were published in Nature Physics in 2024. The bubble nucleated. They watched it form. A small region of the condensate transitioned to the true vacuum state, and the boundary between the two states expanded outward exactly as Coleman and DeLucia's equations from 1980 predicted. Ian Moss from Newcastle University described what the observation meant. Vacuum decay is thought to play a central role in the creation of space, time, and matter in the Big Bang. But until now, there has been no experimental test. Until now, the experiment is not our universe. The condensate is not our vacuum. The scale is incomparably smaller, and the physics of an ultra-cold atomic gas is not the physics of the Higgs field. These are not the same system, and no serious physicist claims the experiment proves our vacuum will decay. What it proves is the mechanism. The mechanism described by Coleman and DeLucia, derived from quantum field theory, predicts that a false vacuum placed next to a true vacuum will produce a nucleation bubble that expands and destroys the false vacuum region. That is what the condensate did. The mechanism works exactly as described. The math that predicted the condensate behavior is the same framework that describes our vacuum. You now live in a world where vacuum decay has been observed in a laboratory. It is in the peer-reviewed literature. It happened. The question is no longer whether a false vacuum can decay in this way. The question is whether ours will and when, and whether the bubble has already started somewhere. Before 2024, you could hold vacuum decay at a comfortable intellectual distance. It was a theoretical prediction, a calculation, a what-if inside a physics paper. It is not a what-if anymore. The process that could end your existence without warning has now been watched in a controlled setting, confirming every detail of the model that says our universe may be next. What do you do with knowledge you cannot act on? The multiverse, as described by eternal inflation, was always supposed to be eternal. The name says it. Inflation goes on forever, producing bubbles forever, in a background that never ends. If the background never ends, the number of pocket universes is infinite. An infinite number of universes means an infinite number of histories, an infinite number of versions of you, in an infinite number of variations, comfortable in its enormity. Infinite problems dissolve into infinite solutions. But in 2003, Arvind Borde, Alan Guth, and Alexander Vilenkin published a paper, and what it shows is that any universe that has been expanding on average, including the inflating background that spawns bubble universes, cannot be eternal into the past. The math is not complicated. Any averaged expanding space-time must have had a beginning. The theorem makes no assumptions about the physics inside the inflating region. It holds regardless of the details. If inflation has been expanding, it started. The inflating background had a beginning. This changes everything quietly. If the machine that produces bubble universes had a start, then there is a finite amount of time the machine has been running. A finite number of bubbles produced before ours. A finite number after, until the machine itself reaches whatever end the math allows. The number could be enormous, 10 to the power of a trillion. More numbers than the atoms in our observable universe, folded into themselves, incomprehensibly large by any human scale. But enormous and infinite are not the same thing. The difference between enormous and infinite is the difference between a thing that runs out and a thing that never does. Infinite means there is always another version of you, always another branch, always another universe in which the situation differs. Finite means there is a count. Somewhere in the math, there is a last bubble, there is a last version. This theorem is confirmed in the sense that its mathematics is accepted. The implications are theory, but the math checks out. Sit with the finite number. A finite number of universes means the copies of you are finite. A finite number of histories means there is no guarantee that a version of you in which things go better exists somewhere in the count. The comfort of infinite chances is gone. The machine had a beginning. Beginnings imply endings. If the machine ends, no new bubbles form. The existing ones expand, cool, and whatever lives inside them moves through their particular version of time until they run out of usable energy. If the number of universes is finite, is there one in which you survive everything? In 1987, Steven Weinberg made a prediction. He predicted the value of the cosmological constant, the term in Einstein's equations that describes the energy density of empty space and controls how fast the universe expands or contracts. He predicted it before it was measured. When measurements came in 1998, He was right. That prediction is one of the most precise, successful predictions in the history of cosmology. Here is what he used to make it. He used the string theory landscape, developed by Leonard Susskind, Qumran Vafa, and Raphael Bousso. The landscape describes the number of possible stable vacuum states that string theory permits. The number is approximately 10 to the power of 500. Each state is a possible universe with its own physics, its own masses for particles, its own strength for forces, its own value for the cosmological constant. 10 to the power of 500 distinct configurations, each one a universe that could exist. Weinberg's method was the anthropic argument. Of all those possible universes, only a narrow range of cosmological constant values permit galaxies to form. If the constant is too large, space expands too fast and matter never clumps. If it is too negative, space collapses before stars ignite. Weinberg asked, given that we exist, what value of the cosmological constant should we expect to observe? The answer he calculated matched the measurement that came 11 years later. This is the price of that prediction. To use the anthropic argument, you must accept that the constants of physics in our universe are not determined by some deeper law that required them to have these values. They are drawn from a distribution. Our universe happens to sit in the part of the distribution where observers can form. If you had landed in one of the other 10 to the power of 500 configurations, you would not be here to notice. You exist because you are in the right part of the lottery. That is the most successful prediction in modern cosmology, and it was made by accepting that nothing about your universe was chosen. The mass of the electron, the strength of gravity, the speed of light, these values work for you because you are here, and you are here because they work. The reasoning is circular in a way that is logically valid and physically devastating. There is no deeper reason the electron has the mass it has. There is no law that required gravity to be this strong. These are the numbers your bubble happened to land on, drawn from a space of possibilities so large that the human mind cannot hold it. You exist by accident. The most accurate prediction of the last 30 years required that conclusion to be true. What does it mean to build a life on a foundation chosen by nothing? Einstein made a mistake in 1917. He knew the math of general relativity allowed the universe to expand or collapse. He didn't like that. An expanding or collapsing universe implied a beginning or an end, and both of those ideas disturbed him. So he added a term to his equations, a fudge factor, a number he inserted to make the universe sit still. He called it the cosmological constant, lambda, a force that pushed outward against gravity, balancing everything perfectly, holding reality in place like a pin through a butterfly. It worked mathematically. The universe, in his equations, became static, eternal, safe. Then, in 1929, Edwin Hubble published his observations. Galaxies were moving away from us. All of them. The universe was expanding. There was no argument. Einstein had added an unnecessary constant to the most important equations in physics because the alternative made him uncomfortable. He reportedly called it his biggest blunder. He removed it. The cosmological constant was abandoned. And then, 1998 happened. Two independent teams, one led by Saul Perlmutter and one led by Brian Schmidt and Adam Rees, were studying distant supernovae. They expected to see the expansion of the universe slowing down over time. Gravity was supposed to be pulling everything back. What they found instead was that the expansion was accelerating. Something was pushing the universe apart faster and faster. Something that behaved, mathematically, exactly like Einstein's abandoned cosmological constant. Einstein had been right, for the wrong reason, using the wrong logic, based on a desire to avoid an uncomfortable conclusion. He had accidentally predicted a real force in the universe by trying to cancel it out. Perlmutter, Schmidt, and Rees won the Nobel Prize in Physics in 2011. The cosmological constant came back. It was renamed dark energy. Lambda CDM, the standard model of cosmology, was built around it. The constant was assumed to be exactly that, constant, the same everywhere, always, for the entire history of the universe. That assumption held for 27 years. Then in April 2025, the Dark Energy Spectroscopic Instrument released its full dataset, 50 million galaxies mapped in 3 dimensions, the most detailed survey of the large-scale structure of the universe ever completed, and the data showed that dark energy is weakening. It is not constant. It was stronger in the early universe, and it is weaker now. The number Einstein inserted to hold reality still is not a number at all. It is a variable. It changes over time. Here is where the logic chain tightens around you. If dark energy is weakening, the equations that describe the fate of the universe change. The current models that predict a slow, cold, eternal expansion are based on lambda being fixed. If lambda is decreasing, the future of the universe becomes harder to calculate. Some configurations lead to a big crunch. Others lead to something stranger, a universe that begins to fold back on itself. And here is the part that should stay with you. Einstein's cosmological constant was, by his own account, his biggest blunder, a mistake rooted in wanting the universe to be something it wasn't, and that mistake turned out to be real, a real force. In a universe he misunderstood. So when the survey tells us that force is now evolving in ways we didn't predict, it's worth asking, what other things do we believe are constant because we need them to be? There is a thought experiment physicists call quantum immortality. It sounds like wishful thinking. It is closer to a trap. In many worlds, the universe branches at every quantum event. Every possible outcome occurs in some branch. You exist in the branch where you are reading this right now. In other branches, other versions of you are reading something else, or doing something else entirely, or no longer alive. Here is the logic, and follow it carefully, because it doesn't lead where you expect. David Deutsch, one of the architects of modern quantum computation and one of the most rigorous defenders of many worlds, worked through the implications of branching for the question of death. His conclusion, and it is a logical conclusion given the premises, is this: from your subjective perspective, you cannot die. When you approach a fatal moment, the universe branches. In most branches, you die. In some branches, you survive. The branches where you die have no conscious observer to experience the death. The branch where you survive does. You will always find yourself in that branch. You will always be the version that made it through. Confirmed mechanism, confirmed quantum branching, theory applied to consciousness. But the math checks out. Every time you have nearly died, you are, right now, in the branch where you survived. The car accident you almost had. The illness that almost turned serious. The moment on the stairs, last winter, when you caught yourself. In every one of those cases, there are branches where you didn't make it. And in every one of those branches, you are not there to notice. But here is where quantum immortality stops feeling like comfort and starts feeling like something else. The branches where you survive get narrower. Every near-death event requires a branch where the physics conspired in your favor. The older you get, the more improbable the survival branch becomes. You are not living a long life. You are being funneled into increasingly unlikely corners of the wave function. The branches around you are thinning. The survival path requires more and more coincidence to sustain. You are not becoming invincible. You are becoming a statistical anomaly. And the branches don't care about your quality of life. They only require that you survive. The branch where you live to 120 but spend decades in diminishing health still exists. The branch where survival comes with costs you wouldn't choose is still a branch. Quantum immortality does not promise a good life. It promises only that subjectively, you will always experience the next moment. This is the philosophical reset this chapter requires. We've been treating death as the worst outcome. Many worlds suggests it might not be, because the alternative, the guarantee that you will always find yourself in the branch where you are still alive, means you are not moving through time. You are being filtered into it, forced along a path that grows narrower with every step, trapped in survival. And here is the question this leaves you with. If you cannot die from your own perspective, and you are currently standing in the thinning end of an increasingly improbable branch, then what exactly are you surviving into? Think about a decision you made yesterday, a small one, whether to reply to a message, which route you took home, what you ate. It doesn't matter which decision. What matters is that you made it. And in doing so, your neurons fired in a particular sequence. Quantum events inside your brain resolved in a particular direction. The wave function of your body collapsed into a specific path. And in many worlds, the other paths still exist. There is a version of you who made the other choice. Who sent the message you didn't send? Who took the other route? Who stayed when you left, or left when you stayed? And that version of you is not a hypothetical. According to many worlds, now taken seriously by a majority of physicists surveyed in formal studies of quantum foundations, that version of you is physically real. They exist in a branch of the wave function that diverged from yours at the moment of that quantum event. Right now, somewhere in the structure of reality, that version of you is continuing their life. They have your face, your voice, your memories, up to the moment the branch split. They don't know they're a branch. From inside their experience, they are the original. They are the one reading the script. They are the one convinced they are real. And from their perspective, you are the branch. Let that settle. There is no experiment that can distinguish you from a branch. The feeling of being the original is not evidence of being the original. Every branched version of you feels exactly what you feel right now. Continuity, selfhood, certainty. Sit with that for a moment, because it gets worse. This is happening 25,000 times per second. Every second, you are branching into thousands of versions of yourself. Each of those versions has your memories. Each of them believes they are you. Each of them will continue to branch. The you that existed 1 second ago has already become tens of thousands of distinct entities, each diverging, each certain of their continuity, each wrong in the same way. The career choice you regret, the relationship that ended, the version of you who made the other call is out there, in a branch, carrying the life you didn't choose, and calling it their life, and they are right to do so. Physicists debate whether branches can interfere with each other after divergence. The standard many worlds position is that they decohere almost instantly. They cannot communicate. They cannot merge back. Once you and your branched self have separated, that divergence is permanent, which means the other versions of you will never know. And neither will you. You are living one thread of a structure that branches wider with every passing second. Every fear you have about the road not taken is, in many worlds, a road someone is walking. Someone with your name, your history, your regrets, your face looking back at them in the mirror every morning. And here is what should stay with you tonight. The version of you in another branch is not thinking about you. They moved on. They have their own life now. They are fine. Are you? Roger Penrose did a calculation. You need to hear the number, and then you need to sit with what it means. Penrose wanted to know the probability that our universe, with all its order and structure, could arise by random chance from a thermal fluctuation, not from a big bang with specific initial conditions, but from pure randomness assembling something that looks like a universe. His answer, published in his work on the second law of thermodynamics and cosmology, was 1 in 10 to the power of 10 to the power of 123. Write that out. 10 raised to the power of a number that is itself 10 to the power of 123. There are not enough atoms in our observable universe to write that number in full, 1 digit per atom. It is not a number you can visualize. It is a number so large that it makes the phrase effectively impossible feel inadequate. And yet, in an eternal universe, given enough time, that fluctuation happens. Given enough space, it has already happened. Everywhere. The argument, first proposed by Ludwig Boltzmann in the 19th century and revived by modern cosmologists studying the long-term fate of the universe, is that in a sufficiently large and sufficiently old universe, Random quantum fluctuations will occasionally produce any configuration of matter, including a brain. Including your brain. A Boltzmann brain is a structure that assembles from random fluctuation with the full complement of memories, sensory experience, and subjective continuity of a conscious human being. It appears, it experiences, it has a past that never happened, and then, in most cases, it dissolves back into randomness within seconds. Here is the problem. This is confirmed statistical mechanics applied to an infinite universe. The math checks out. If the universe is large enough and old enough, and current models suggest it may well be, Boltzmann brains will eventually outnumber genuine observers. There will be more brains that assembled from chaos with false memories than brains that grew from actual biological history, which means that, in a statistical sense, if you had to guess whether any given conscious observer was genuine or a Boltzmann brain, you should guess Boltzmann brain. You should guess that about yourself, your memory of your childhood, your sense that you have lived the years leading up to this moment, your certainty that there is a continuous history behind you. None of that is verifiable from inside your experience. A Boltzmann brain assembled 1 second ago would have identical experiences, would feel exactly the continuity you feel now. The standard philosophical response is to say that the memories feel real, the physical world checks out, and so you are probably genuine. But that response assumes the physical world you're checking is the same one that produced you. A Boltzmann brain's physical world would also check out, because it appeared inside a consistent physical environment. Your belief that you have a past is not evidence that you have a past. And if you are a Boltzmann brain, then everything you think you know, every person you think you've loved, every place you think you've been, assembled from nothing 1 second ago, and you are already dissolving. Is there a version of that idea that doesn't end in dissolution? Or are all of them just different ways of describing the same absence? Stop. Before the next chapter, you need a moment to look at what has been built. You are branching 25,000 times per second. That is confirmed quantum mechanics. Each branch is physically real. Each contains a version of you with your memories, your sense of self, your certainty that they are the original. A mirror version of you may exist in a universe where time runs in the opposite direction, where matter and antimatter switched, where the laws of physics are reflected and reversed, not metaphorically, physically. CPT symmetry allows it. The math requires something to balance the matter asymmetry we observe. A Boltzmann brain with your complete memories could have assembled from quantum noise 1 second ago. The probability is absurdly small, but in an eternal universe it is not zero. And if the universe is large enough, such brains exist somewhere. They feel exactly what you feel right now. There are 10 to the power of 500 string theory configurations. Each one a different universe with different physical constants, different particle masses, different laws. In some of them, something that calls itself you also exists. Now, here is the question all of that forces. What is the you that is experiencing any of this? Consciousness, as you experience it, assumes a continuous observer. The same self that woke up this morning is the self reading this now. That is the intuition. That is how experience feels. Unbroken, singular, yours. Physics provides no mechanism for that continuity across branches. When you branched 25,000 times in the last second, there was no thread that connected the branches. No signal passing from one to the next, saying this is the real one, carry the self forward. The branches simply happened, each one with a complete copy of your sense of continuity, each one wrong about being the only version. The philosopher Derek Parfit spent decades working on personal identity and came to the conclusion that the self is not a deep fact about the world. It is a useful fiction, a narrative we impose on a sequence of physical states that have no inherent continuity. Many worlds makes Parfit's conclusion look conservative. You are not a person moving through time. You are a pattern that keeps splitting, and each copy inherits the memory of being whole. The sense of being you is not a property of physics. It is something you are doing to the data, and the data supports every version equally. Here is where this becomes unbearable. You cannot step outside the branch to check. You cannot verify that you are the original. You cannot find the thread of continuity, because there is no thread. There is only the experience of continuity, and every branch has that, and none of them earned it. There is no physical theory that explains why you are this branch. The one reading this right now, the one who woke up this morning in that specific body in that specific room, why this one? Why not the one that branched off from this moment 3 seconds ago? Why not the one that branched 2 hours ago? Physics has no answer, and the question is not a philosophical curiosity. It is a structural gap in our understanding of what reality is. In December 2024, Adam Rees published new results from the James Webb Space Telescope combined with continued Hubble Space Telescope data. Rees has been working on the Hubble tension since it first emerged clearly in 2013. He has spent over a decade checking and rechecking every possible source of measurement error, new calibrations, new reference stars, new data pipelines. His team's conclusion: there is no measurement error that explains the discrepancy. The tension is real. The Hubble tension is this. When you measure the expansion rate of the universe using the cosmic microwave background, the light from the earliest moments after the Big Bang, you get one number. When you measure it using nearby supernovae and Cepheid variable stars, you get a different number. The two numbers disagree by about 9%, at 5 sigma confidence. 5 sigma means there is approximately a 1 in 3.5 million chance the discrepancy is random noise. This has been confirmed by multiple independent teams using multiple independent methods. The two answers are both correct as measurements. They just disagree with each other. Something is wrong with the standard model, or something happened in the universe that the standard model doesn't account for. The conventional explanations were ruled out one by one over the past decade. Dust calibration errors, instrument drift, selection bias in the supernova datasets, all checked, all ruled out. What remains are the exotic proposals. Some physicists propose early dark energy, a burst of additional energy density in the early universe that briefly changed the expansion rate before fading. Some propose extra-relativistic species, additional particles beyond the standard model that were present in the early universe. And some, and this is the proposal that connects to everything else covered in this script, propose that during the inflationary epoch, our universe's expansion was briefly affected by gravitational interaction with a neighboring bubble universe. This is theory. The math permits it. The evidence does not yet distinguish it from other explanations. But consider the chain. The universe expands. We measure the expansion. We get two different answers. The difference is real. The best mundane explanations are gone. What's left requires physics we don't have yet. And one of the candidate explanations is that the geometry of our early universe was deformed by something outside it, something that touched us before we had the physics to notice. Here is what makes the Hubble tension so unsettling compared to other open problems. Most unresolved questions in physics are about things we haven't measured yet. The Hubble tension is about something we have measured, carefully, repeatedly, with the best instruments humans have ever built. The James Webb Space Telescope represents decades of engineering and billions of dollars spent to see farther and with more precision than any instrument before it. Rees's team used it. The number still doesn't match. At some point, precision stops being the answer. At some point, two irreconcilable measurements stop being a calibration problem and become a statement about the universe itself. Physicists are not there yet. They are still looking for a conventional explanation. But the space for conventional explanations is shrinking. The expansion rate of the universe gives two different answers. Both measurements are correct. Both cannot be simultaneously true under any model we currently have. And the universe is not in the business of waiting for us to figure it out. What does it mean that the fundamental rate at which space itself is growing cannot agree with itself? The Dark Energy Spectroscopic Instrument is a spectrograph mounted on a 4-meter telescope at Kitt Peak National Observatory in Arizona. It has been running since May 2021. It captures the spectra of up to 5,000 galaxies simultaneously. By April 2025, it had mapped 15 million galaxies across 11 billion years of cosmic history, producing the largest three-dimensional map of the universe ever constructed. The map is not decorative, it is a measurement device. By tracking how galaxies cluster at different distances, the survey measures the imprint of sound waves from the early universe frozen into the large-scale structure of matter. This is called baryon acoustic oscillation. It is one of the most precise rulers in cosmology, and the instrument uses it to measure dark energy across billions of years. The first results, released in April 2024, showed dark energy deviating from the cosmological constant at 2.5 sigma. Interesting, but not definitive. The 2025 results, incorporating a second full year of data, show the deviation at 4.2 sigma. That is past the threshold astronomers use to claim a probable detection. Dark energy is not constant. It was stronger in the past, and it is weaker now. The standard model of cosmology, built around a fixed cosmological constant and cold dark matter, fits the survey data significantly worse than models where dark energy evolves over time. The trend is getting stronger with more data. Every new galaxy the instrument maps is a new data point. Every new data point makes the fit between the standard model and reality slightly worse. Here is what that means for you, sitting where you are right now. The model used to calculate the age of the universe, the rate of its expansion, the timeline of its past, and the trajectory of its future was built on an assumption that dark energy does not change. Every calculation made under that model is based on a fixed lambda. If lambda is not fixed, those calculations need revision. The universe you have been told about is a universe modeled under an assumption that appears to be wrong. Physicists are cautious. They say the data needs more analysis, more cross-checks, independent confirmation. That is correct scientific practice. But 4.2 sigma is not a rounding error. It is a signal, and it is getting louder. Lambda CDM has been the dominant cosmological framework for 27 years. It has survived every test thrown at it, except one. And now that one exception is accumulating evidence every night the survey runs. The thing Einstein called his biggest blunder turned out to be real. Then it turned out to not be constant. Every new observation tells us we understand it less than we thought. What does the universe look like when the model we use to describe it starts disagreeing with the universe itself? The Antarctic Impulsive Transient Antenna is a balloon-borne instrument that circles Antarctica at high altitude, listening for radio pulses from cosmic ray events. It detected two anomalous signals, one in 2016 and one in 2018. The signals came from below, from inside the Earth. But the particles that could produce those signals, high-energy tau neutrinos at the energies detected, cannot travel through the Earth at those energies. The standard model says they should be absorbed long before emerging on the other side. Those signals are still unexplained. Confirmed detection, confirmed anomaly. Several proposals exist, including sterile neutrinos, dark matter, physics beyond the standard model. None has been confirmed. The anomaly remains open. Rangaram Chari of the California Institute of Technology published a paper in 2015 analyzing a region of the cosmic microwave background where the signal was significantly brighter than take surrounding areas. After subtracting all known foreground sources, a residual blob of light remained. Chari's controlled interpretation was that it might be a collision scar from a bubble universe. Other physicists proposed unaccounted foreground dust, but the blob persists in the data. As of the most recent analyses, it remains anomalous. Alexander Kashlinsky and his team have spent years measuring what appears to be a large-scale flow of galaxy clusters. moving coherently toward a specific region of sky. The velocities are too large to be explained by the visible matter distribution in our observable universe. Dark flow, if real, suggests a gravitational source beyond our cosmological horizon. The proposal is contested. The signal has not been independently confirmed to everyone's satisfaction, but it has also not been refuted. The cosmic microwave background cold spot is a region of the sky roughly 1 billion light-years across that is measurably colder than its surroundings. The expected temperature variation for a region that size is far smaller than what is observed. The leading conventional explanation was a supervoid, a vast underdense region between us and the cold spot that could cool photons passing through it. That explanation was ruled out by galaxy surveys in 2015 and confirmed insufficient by further analysis. The cold spot remains without a satisfactory conventional explanation. 4 separate anomalies, 4 different instruments and research teams, 4 different regions of sky or particle channels, all still open, all still accumulating data. None resolved. The universe is not sitting still while we work on these problems. The instrument continues to fly. Surveys continue to map the cold spot region. Koszaliński continues refining the dark flow measurements. Cherry's blob region has been re-examined with newer instruments. The anomalies arrived at different times using different methods. They point in different directions. They may be unrelated, or they may all be pointing at the same thing, something outside the standard model, or even outside our observable universe, from different angles and with different instruments, and we do not yet have the framework to see what they have in common. The universe is sending signals. We receive them. We record them. We do not understand them. They are not from the past. They are arriving now. Roger Penrose is one of the most decorated mathematical physicists alive. He collaborated with Stephen Hawking on singularity theorems in the 1960s. He invented twistor theory. He has spent the last 2 decades developing what he calls conformal cyclic cosmology. The proposal is this: our universe will eventually reach a state where all matter has been consumed by black holes. All black holes have evaporated through Hawking radiation, and what remains is a featureless, expanding sea of radiation. At that point, the universe has no scale. There are no massive particles to define distance or time, and Penrose argues that a universe with no scale is mathematically equivalent to a universe at the Big Bang. The conformal geometry matches. One state feeds into the next. Our universe is not the first. It is one in an infinite chain of universes, each arising from the dying state of the previous one. Each cycle, Penrose calls an aeon. The prediction that distinguishes this from pure speculation is the existence of what Penrose calls Hawking points. In the previous aeon, supermassive black holes evaporated over enormous timescales, releasing their energy as concentrated bursts of radiation. That concentrated energy, Penrose predicts, should have left a faint but detectable imprint in our Big Bang, carried through the conformal transition. It should appear in the cosmic microwave background as slightly warmer rings of low-variance regions, Hawking points. In 2018, Daniel Ahn, Christoph Meissner, Paweł Narowski, and Penrose published a paper claiming to have found these points in the Planck satellite data of the cosmic microwave background. The statistical significance was contested. Other teams argued the patterns could be explained by chance. The debate continues. But here is what this means for the cold spot. If conformal cyclic cosmology is correct, the cold spot in the cosmic microwave background might be a Hawking point from the previous aeon, an imprint from a black hole that evaporated in a universe that died before ours began, a signal that crossed the conformal boundary, something from a dead universe already inside ours, not beside us, before us. A universe whose entire history, billions of years of stars and galaxies and whatever arose in them, compressed itself into a final radiative state and then transitioned into the conditions of our Big Bang. Its death was our birth. And if that is true, the cold spot is not empty. It is an echo, not of something that happened long ago in our universe, but of something that happened before our universe existed. A scar from the previous world carried through the seam. You have looked at images of the cosmic microwave background. You may have seen the cold spot without knowing what it might be. It is already inside every map of our universe's earliest light, already present, already measured. If Penrose is right, something from before our universe is already here, right now, waiting in the data we already collected. The question is what it is waiting for. Nothing in this script has been resolved. The Hubble tension is still open. Adam Rees and his collaborators confirmed in December 2024 that it is real, that measurement error cannot explain it, and that whatever causes it lies outside the current standard model. No proposal has been confirmed. The two measurements of the expansion rate still disagree. The dark energy signal is still strengthening. Every night, the survey runs. More galaxies are mapped. The deviation of dark energy from a cosmological constant is at 4.2 sigma and climbing. The trend has gone in one direction across every data release. Lambda CDM fits the universe worse with every new measurement. The upward traveling particles are still unexplained. The anomalous signals from 2016 and 2018 have not been matched to any confirmed source. The proposals remain theoretical. No experiment has closed the question. The cold spot in the cosmic microwave background is still there. The supervoid explanation was ruled out. Conformal cyclic cosmology offers an interpretation, but the statistical evidence for Hawking points is contested. The cold spot remains a measured anomaly without a satisfactory account. Koszaliński's dark flow remains unconfirmed and unrefuted. The bright blob Chari identified in the cosmic microwave background residuals remains anomalous. The false vacuum has not decayed, as far as we know, which means as far as any measurement within our light cone can tell us. These are not old questions waiting to be cleaned up. They are active. Instruments are running right now. Data is being collected. Papers are being written. Every week produces new measurements that either deepen the anomalies or add new ones. The signals are ongoing. Here is what was asked at the beginning of this script. Another reality is leaking into ours. Is that true? The honest answer is that we do not know what the anomalies mean. Some may have mundane explanations not yet identified. Some may require new physics entirely. Some may require something that does not yet have a name. But here is what is true right now. As you are sitting where you are, as your atoms are branching 25,000 times per second, as the universe is expanding at a rate that disagrees with itself, as dark energy weakens across a map of 15 million galaxies, as the instrument listens from above Antarctica, as the cold spot sits in every image of the cosmic microwave background ever made. The word reality has a specific meaning in physics. It refers to the set of physical laws and structures that govern the behavior of matter and energy in a consistent and predictable way. Every anomaly covered in this script is a place where that consistency breaks down, where the predictable gives a wrong answer, where the measurement doesn't fit the model. When enough of those places accumulate, you stop calling them anomalies and start asking whether the model is wrong about something foundational. Whether the structure we call reality is one of many structures, whether what we observe is not the whole thing, but a region within something larger, something that touches our region at specific points, leaves specific marks, and does not obey the same rules. The dark flow is still pulling. Whatever is pulling it is beyond our cosmological horizon. We cannot see it. We can only see the direction it pulls. And right now, every instrument we have pointed at the sky is returning data that fits our models a little less well than it did